The Falcon Heavy is currently the most powerful rocket in existence, with the ability to lift a payload of nearly 64 metric tons into orbit. SpaceX first demonstrated the capability of the Falcon Heavy back in February of 2018 when they successfully launched a Tesla Roadster into space, and the first commercial flight is scheduled for April of 2019. The first stage of the rocket consists of 3 Falcon 9 Block 5 boosters that are connected together, each with 9 Merlin rocket engines. The second stage uses a single Merlin engine, and it is carried on top of the center core of the first stage. SpaceX is continuously working to improve their Merlin rocket engines, and as a result, the second iteration of the Falcon Heavy is now even more powerful than before. It is difficult to predict exactly how much power is generated by the rocket, but today we will use some simple calculations to estimate the peak power that can be produced at liftoff. Let's start by taking a look at the figures for a single Block 5 Merlin engine. A single engine can generate a maximum thrust of 903 kilonewtons in Earth's atmosphere with a specific impulse of 2,844 newton-seconds per kilogram. We can calculate the mass flow rate, m-dot, by dividing the thrust by the specific impulse. This mass flow rate is the rate at which the engine will consume fuel, and we find that one Merlin engine will consume 317.5 kilograms of propellant every second. The Falcon Heavy has 27 engines in total, so we can calculate the mass flow rate for the entire rocket by multiplying the value for a single engine by 27. In reality, the 9 engines of the center core do not operate at full power during liftoff, but we will neglect this to calculate the theoretical maximum power output. If all 27 engines are operating at full thrust, then the entire rocket will consume propellant at a rate of 8,573 kilograms per second. The propellant used by the Falcon Heavy is called RP-1, and it is a highly refined form of kerosene with an oxidizer to fuel ratio of 2.56. This means that every kilogram of propellant will contain 0.28 kilograms of kerosene and 0.72 kilograms of oxidizer. The gross heat of combustion of kerosene is 46.2 megajoules per kilogram, and we can calculate the gross heat of combustion of the propellant by multiplying this value by 0.28 to account for the oxidizer to fuel ratio. We can now calculate the power output of the rocket by multiplying the gross heat of combustion and the mass flow rate, which gives about 111 gigawatts, or just under 150 million horsepower. This figure is an estimate of the total power output of the rocket at liftoff, without accounting for efficiency. To put this kind of power into perspective, the Three Gorges Dam in China has a peak generating capacity of 22.5 gigawatts, and it supplies power to 9 provinces and 2 cities, including Shanghai, which is the largest city in the country. This hydroelectric facility is the largest power generation plant in the world, yet it would take 5 of them to produce the same amount of power as a single Falcon Heavy rocket. Delivering large payloads into space requires huge amounts of energy, and if you want to lift the weight of a fully loaded 737 jetliner, then you need to use the most powerful vehicle available, the Falcon Heavy. Hey everyone! I hope you enjoyed today's video about the Falcon Heavy rocket. Please subscribe if you want to see more engineering videos from this channel, and check out my Patreon page if you want to get early access to videos and other content. Thanks for watching, and I'll see you in the next one.